All right, welcome everyone. Today we are diving into one of the biggest, most mind-bending ideas in all of science for this special exam review explainer, Einstein's relativity. So, let me ask you something. Why on earth does your GPS need a theory that's over 100 years old just to work? We're going to start right there with a smartphone in your pocket and see how this amazing piece of tech is totally reliant on Einstein's genius. So here's the plan. First, we'll look at the crack in old physics that got this whole thing started. Then, we'll get into the difference between special and general relativity. After that, we'll see how scientists actually proved Einstein was right. And finally, we'll bring it all back to that gadget in your pocket. Sound good? Let's get into it. Okay, so let's set the scene. We're going back to the turn of the 20th century. For like 200 years, everybody thought Isaac Newton had it all figured out. His laws of physics, they were rock solid. But there was this one little nagging problem, this one stubborn fact about light that just didn't fit, and it was about to blow everything wide open. And this puzzle was a huge deal. I mean, think about it. If you're on a speeding train and you throw a baseball forward, its speed is the train's speed plus the speed you threw it at, right? Simple addition. But light just didn't care about the rules. It didn't matter if you were standing still or flying in a spaceship at incredible speeds. If you measured the speed of light, you got the exact same number. Every single time. This one observation completely shattered the foundations of old-school physics. So, scientists had this idea, right? They thought light waves must travel through something, some invisible stuff they called the ether. The famous Michelson-Morley experiment was designed to prove it existed by measuring Earth's movement through this ether. But the experiment was a total failure, or, well, a stunning failure. They found nothing. No ether, no motion. And the only way that made sense was if the speed of light was always constant, which meant our entire understanding of space and time had a major flaw. And this is where a young patent clerk named Albert Einstein steps onto the scene. He looked at this puzzle and came up with not just one, but two groundbreaking theories that completely changed how we see the universe. So let's break down the difference between them. So you gotta remember, these came out 10 years apart. First up, in 1905, was special relativity. And it's special for a reason. It only deals with a special case, things moving at a constant speed, no acceleration. Einstein knew this wasn't the full picture because, what about gravity? What about speeding up and slowing down? That took him another 10 years of work to figure out, leading to his masterpiece, general relativity, which totally rewrote the rules on gravity. Okay, now we get to one of the wildest ideas to come out of special relativity, time dilation. And yeah, it's pretty much what it sounds like. The faster you go, the slower time ticks for you compared to someone who's stationary. It's straight out of science fiction, right? But here's the kicker. It is 100% real. And how do we know it's real? Because we've tested it. They literally put super precise atomic clocks on airplanes and flew them around the world. And guess what? When they landed, those clocks had ticked just a tiny bit slower than the ones left on the ground, exactly as Einstein predicted. We even see it with particles from space called muons. They shouldn't live long enough to reach Earth's surface, but they do, all because time slows down for them at their incredible speeds. All right, now for the big one, general relativity. This was Einstein's true masterstroke. He said, forget everything you know about gravity. It's not some invisible force pulling you down. No. He proposed that huge objects, like planets and stars, actually bend and warp the very fabric of reality itself, a four-dimensional fabric he called spacetime. There's this fantastic quote by the physicist John Wheeler that just nails it. He said, "Spacetime tells matter how to move. Matter tells spacetime how to curve. It's this beautiful, perfect loop. The stuff in the universe creates the curves, and the curves tell the stuff how to travel." You've probably heard the classic analogy, and it's a great one. Imagine a big, stretchy trampoline. Now, drop a heavy bowling ball in the middle. What happens? It creates a big dent, a curve in the fabric. If you then roll a little marble nearby, it doesn't get pulled by the bowling ball. It just follows the curve. For Einstein, that's all gravity is. The Earth isn't pulling you down, it's just curved space-time around you, and you're following that curve. So, okay, these ideas are massive, right? Almost unbelievable. So how on earth did scientists go about proving any of this was actually true? Well, it wasn't a one-and-done thing. It took decades. See, the beauty of Einstein's theories is that they made very specific, very testable predictions. And over the years, experiment after experiment came back with results that matched those predictions, each one adding another solid piece of evidence to the pile, all pointing to one conclusion. Einstein was right. But the first major confirmation of general relativity, now that was pure drama. Einstein made this incredibly bold prediction. He said the sun is so massive that its gravity should literally bend the fabric of spacetime around it, so much so that it would actually change the path of light from distant stars passing by. A wild idea and one that was super difficult to test. So, in 1919, a team led by astronomer Arthur Eddington went on an expedition. They waited for a total solar eclipse, the only time you could see stars close to the sun. And with the sun's light blocked out, they took pictures. And what did they find? The stars weren't where they were supposed to be. Their positions had shifted because the sun's gravity had bent their light precisely, as Einstein's math said it would. The news exploded. It was front-page stuff all over the world. Einstein became a superstar overnight. Okay, so we've gone through the old physics, the two new theories, and the proof that made Einstein famous. Now let's circle all the way back to the beginning. Back to that phone in your hand. How does all this mind-bending physics actually guide your GPS? Okay, this is so cool. Your GPS relies on super accurate clocks on satellites, but those satellites are living in a relativistic world. So two things are happening at once. First, special relativity. Those satellites are zipping around the Earth at about 14,000 kilometers an hour. That speed makes their clocks tick just a little bit slower than ours, by about 7 microseconds every day. But wait, there's more. General relativity comes into play too. The satellites are way up high, where Earth's gravity is weaker. And weaker gravity means time actually speeds up, so their clocks tick faster than ours by 45 microseconds a day. The engineers have to combine those two effects and correct for that net 38 microsecond daily drift. So, 38 microseconds. That sounds like nothing, right? Who cares? Well, your GPS cares. A lot. Because if we didn't correct for that tiny little time difference, the errors would build up fast. After just one day, your GPS would think you are 10 kilometers away from where you actually are. It would be completely, utterly useless. So yeah, relativity isn't some abstract idea for physicists to debate. It's practical, essential engineering that you use every single day. And that really brings us to a final, pretty amazing thought. 100 years ago, a guy asking a deep, fundamental question about the speed of light ended up giving us the technology for GPS. It makes you wonder, doesn't it? What current, seemingly abstract scientific puzzles, the ones scientists are grappling with right now, what incredible technologies will they unlock for the world 100 years from now?